Today we are actually discussing an example for time independent non-degenerate perturbation theory which we discussed yesterday. So in this example we will be discussing the well-known Stark effect. Which is as you know the effect that an external electric field has on the energy levels of an atom. So let's assume that there exists some electric field along the positive z direction. So we can write the electric field as the field along the z direction. Now let's consider a hydrogen atom which is placed in an external electric field which is acting along in this vertical direction. So as you know, for a hydrogen atom we have a positive nucleus and an electron which is revolving around that nucleus. So the unperturbed Hamiltonian of the system, the unperturbed Hamiltonian means the Hamiltonian of the system in the absence of this electric field. So the unperturbed Hamiltonian of the system can be written as H0 equal to the kinetic energy part, the p square by 2 mu, and then the potential energy part. The potential energy part means 1 by 4 pi epsilon 0 into E square by R. Okay, so this mu is the reduced mass of the system, as you know, which involves the mass of nucleus and the mass of electron. Now for simplicity we put this quantity 1 by 4 pi epsilon 0 can be taken as some constant, let's say k. So this expression will become a much simpler one, so you can write it as p square by 2 mu minus k e square by r. Yeah. So if we express these operators in means these observables, that means the momentum in operator form, this will become minus h cross square by 2 mu into del square minus k e square by r. So that is the unperturbed Hamiltonian H0. Okay, so remember yesterday we were discussing that the Hamiltonian of the system should be capable of writing something like as a contribution from the unperturbed part and the contribution from the perturbed part. So out of this unperturbed Hamiltonian of the system is given by this expression. So this is the case when there is no electric field act in this space. So the eigenfunction of this Hamiltonian can be written as, let's say, psi n l m. So we had discussed the eigenfunctions of the hydrogen atom in previous semester. So this is given by this is a function of r, theta and phi, and we have three quantum numbers n, l and m. So this is a product of a radial part which is given by r and l of r, and then the spherical harmonics y, l, m, theta, phi. So we have seen it in the previous semester. So this is the solution for the unperturbed Hamiltonian of the system. So now suppose that we have switched on this electric field. Now if you switch on the electric field, the electric dipole moment of the atom start interacting with the field, giving an additional potential energy to the electron. So what is that potential energy due to this dipole? So the dipole is given by the charge into distance, right? So we have, so if we take the separation between this nucleus and the electron as r, then we know that the dipole moment is given by minus ER. So that is the dipole moment of the atom. Now it starts to interact with the applied electric field, right? So it starts to interact with the applied electric field, and this will give the product of the negative of the dipole moment, and this electric field will give us an additional potential energy term, right? So this is an additional potential energy term. So this is going to be the perturbation Hamiltonian of our system. So we can write the perturbed part of the Hamiltonian, HP, is equal to this thing. So that is ER into Z, right? So that Z comes from, because this electric field is acting along this direction, along the direction of K. So what we have is, basically we have, and when you take the product between E dot R, so this is also a vector quantity, right? When you take the product between E dot R, then this electric field, and then out of these XYZ components, only the Z components will give you the non-zero value. So this is E into Z. So this is the electronic charge, and this one is the electric field, and this one is not the unit vector. It should not be confused with the unit vector. This is the Z direction, means the position or the distance along the Z axis. Okay. So the total Hamiltonian of the system is now given by H equal to minus H cross square by 2 mu del square minus K E square by R plus E into Z. So this is the total Hamiltonian of the system when you switch on the electric field, and this part constitute H0, and this part will be the perturbed part of the Hamiltonian, HP. So this is exactly similar what we were discussing yesterday. The Hamiltonian should be capable of splitting into two parts. One is the non-perturbed Hamiltonian, and the other one is the perturbed Hamiltonian. And we assume that the contribution of this term is very small compared to the contributions from the unperturbed part of the Hamiltonian. Now, since the excited states of hydrogen atoms are degenerate, we cannot use this non-degenerate perturbation theory to analyze the excited states. However, we know that the ground state is not a non-degenerate state. So non-degenerate perturbation theory can be applied only to the ground state of the hydrogen atom. So what is that ground state? Ground state is when your quantum number n is equal to 0. When n equal to 0, L will be 0, and M will also be n equal to, the ground state is going to be n equal to 1, and when n equal to 1, L will be 0 and M will be 0. So the ground state of the hydrogen atom can be represented as psi 1 0 0 NLM. So psi 1 0 0 is the ground state of the hydrogen atom. Now the energy of this system to second order perturbation, if you include terms up to second order perturbation, we can write it as, this energy is En, can be written as En0, that is the energy from the unperturbed part of the Hamiltonian. And then we had, if you remember what we discussed yesterday, we have terms like Yn0 HP, Yn0 HP, Yn0 plus sigma n not m not equal to n psi m0 hp psi n0 the modulus square divided by En0 minus Em0. So this was the expression that we have seen yesterday for the energy eigenvalues using the non-degenerate perturbation theory. Okay, so this is the first order correction time, and this is the second order correction time, and this is the unperturbed energy of the system. Okay. Now in place of En, what we are going to do right now is we are trying to find out the correction in the ground state of the hydrogen atom. So we can write it as E100, then En0 is given by E100 in the unperturbed condition, and for this, what is the perturbed Hamiltonian here? The perturbed Hamiltonian is given by this quantity, right? E into Z. Okay, so we can write this expression as E100 equal to E1000 plus E into this psi n0 state is given by for notational simplicity we can write it as simply as 100. So that is our one state. Then search 100 plus E square into capital E square NLM not equal to 100, then NLM search 100 divided by E1000 minus ENLM 00. So this is the expression which we have to evaluate to find out the correction in the energy of the ground state of the hydrogen atom. Okay, so this is exactly same as this one, this expression. The only thing is that we have made some substitution, like the perturbed Hamiltonian is given by this expression. So wherever you have this HP, we have to write EE into Z. So that is what we have written here, EE into Z. So these have been taken outside this integral because these are subscalar quantities. Here also we have the square of that things. So we have E square, capital E square. Now this index, in place of index M, we have these quantum numbers N, L, M. We have to consider the effect from all these quantum numbers N, L, M. So we have written it in this way. Okay. Now, so we have to evaluate this integral to find out the correction. Now the term, let's first consider the term 100 Z 100. So this is basically what we have is an integral psi 100 square surge into d cube r. Okay, because 100 is basically psi 100. I have written 100 just for notational simplicity. So this is going to be, as you know, this is 0 because this is considering the parity of the system. because this one has an odd parity. If you remember the parity, the discussion on the parity that we had in the previous module, and if you try to find out the parity for this hydrogen atom, you can see that the parity of psi NLM theta phi is given by -1 all raised to L psi NLM. Now for M prime, L prime, M prime, Z NLM, the matrix elements, the parity is given by -1 all raised to L prime plus L plus 1, then N prime, L prime, M prime, Z N L M. So this is the parity coming from this L prime, and this is the parity coming from this L, and this is the parity of this Z operator or the position. Okay, so this is an odd parity, right? So if you see 1 0 0 Z prime 1 0 0, the parity is given by both our L and L prime are 0, so the parity is given by -1 raised to 1. So this is simply -1. So we know that it has an odd parity. The ground state of the hydrogen atom has an odd parity. So for this odd parity integral, this will vanish. That integral will vanish. So we have seen that this product simply goes to 0. Means this integral simply goes to 0. So this means that there can be no correction term to the energy which is proportional to the electric field, and hence we say that there is no linear Stark effect. And the physics behind this is that when the hydrogen atom is in its ground state, it has no permanent electric dipole moment, so it is not going to be affected by the external electric field. For the linear Stark effect is not there. Okay. So we are left with only a quadratic dependent term. This correction is usually known as the energy shift, delta E. This correction to the ground state is usually known as the energy shift, and let's put it as delta E. We can write delta E equal to E square sigma N L not equal to 1 0 0 N L M Z 1 0 0 the modulus square divided by E 1 0 0 minus E N L M 0. Now if you remember, the energy of the hydrogen atom is given by the expression En equal to minus E square by 2A0 into 1 by N square, where this A0, which is called the Bohr radius, is given by 4 pi epsilon 0 h cross square by m e square. So these things we have seen in previous semester. So let's calculate the energy difference between some of the energy levels of the hydrogen atom. So E100 minus E200 is given by E square by 2A0. Then what we have is -1 plus 1 by 4. So this will be minus 3 e square by 8 a0. Similarly, the difference between E100 and the next higher state E300 is given by e square by 2a0. Then we have minus 1 plus 1 by 9. N is equal to 3. So n square will be 1 by 9. This is given by minus 4 e square by 9 a0. What you can conclude from here is that for n greater than or equal to 2, we have E100, the difference between E100 minus ENLM0 will be less than or equal to 3e square by minus 3e square by 8a0, because if you take the energy difference between E100 and the next higher level, that is E400, then you are going to get a number which is again less than this one. Okay, so all the successive such terms will be less than the previous term. So in general, we can write the energy difference between the ground state and any of the excited state will be always less than 3 square by 8a0, and this is equal to minus 3 square by 8a0 when you consider the energy difference between the ground state and the first excited state. Okay, so this will help us to write the energy shift delta E as delta E is given by, write it as minus of 8a0 e square by 3 sigma NLM not equal to 100 NLM set 100 the modulus square. Okay, because we have substituted for this denominator the energy difference E100 by this quantity by 3 square minus 3 square by 8a0. So let's see what is this integral. Sigma NLM not equal to 100 NLM set 100 square. So this is, we can write it as sigma for all NLM set 100 square. Here we actually included all states including the 100 state. This can be done because we have seen previously that this integral basically 100 set 100 is 0 because of the parity, because of the odd parity of the system. So this is 0. So the right hand side can be written as sigma or NLM 100 set NLM, then NLM set 100. Right. So we have written it as the product of two expressions. One is the complex conjugate of the other one. So this is equal to, we can write it as 100 set. So now we take this summation to inside this part. So we can write it as sigma or NLM, then NLM NLM Z100. Okay, so now you can see that these things within the bracket is 1, right? So because we know that the states NLM state, the set of states, it form a complete orthonormal set of bases. So this is basically the identity statement for that NLM basis. So this is simply 1. That means you can write this expression as this is 100 set. Then we have one more set here, so you can write it as 100 set square 100. Okay. Now if you make some substitutions, like let's change the coordinates to the from the Cartesian to the spherical polar coordinates, then you can write z is equal to r cos theta and r theta phi 100 is given by the product between the radial part r10 and the spherical harmonics. So here both the L and M are 00 theta phi. So this integral, this expression 100 z square 100 is, if you evaluate this integral, it is given by integral 100 r theta phi the modulus square because of contribution from these two terms. Then we have z square, then dr d theta d phi. So if you make the substitution for z square in polar coordinates or in spherical polar coordinates, you can write it as, so psi 100, so this is r 10 0 for the non-degenerate state. Then we have the spherical harmonics y 00 theta phi, so this is a function of r alone. And then we have r square cos square theta dr d theta d phi. Now if you evaluate this integral by putting the values of the radial function and the spherical harmonics for these quantum numbers, and if you do that integration, what you get is you simply get a0 square. So we can take that integral result. So this quantity simply gives you a0 square. So the energy shift delta E is given by minus 8 a0 e square by 3 into a0 square. So this will become minus 8 by 3 a0 cube into e square. Therefore the ground state energy corrected to the second order is given by E100 is equal to E100 the unperturbed energy minus 8 by 3 a0 cube e square, and we have seen that there is no linear Stark effect possible. So the contribution, there is no first order correction. This is the unperturbed energy and this is the second order correction. First order correction is 0. So this is the energy corrected to the second order for the hydrogen atom. Now as the correction is proportional to the square of this electric field, this is usually referred as the quadratic Stark effect. Quadratic Stark effect, as it is proportional to the square of the electric field. Now, once you know the energy shift, basically we can calculate the polarizability of the hydrogen atom as well. So, if you are interested in the polarizability of the hydrogen atom, let's put it as alpha, is given by minus 2 delta E by E square. So since we know the value of delta E, this can be written as minus 2 by E square into minus 8 by 3 A0 cube E square. So alpha is given by 16 by 3 A0 cube. So that is the polarizability of the hydrogen atom. So we have successfully used the time independent non-degenerate perturbation theory for estimating the correct ground state energy of the hydrogen atom in the presence of a small perturbation, that is in the presence of a small or a weak electric field. So that is given by this particular expression. Okay.